All right. We were talking chapter three, and we kind of jumped into that based on the lab schedule. And kind of in chapter three, we're really talking about electrons, and sort of what we've been talking about is sort of how electrons sort of move from one energy level to the next. And we talked about this idea that, again, much like we did in the flame test, as the atom gains energy, we will see electrons really sort of progress to a higher energy level. They will eventually sort of relax themselves back down. The result of that, as we talked about, is energy from the atom will basically be given off as the electrons go from a higher energy level to a lower energy level in an exothermic sort of process for our atom, where it's going to release energy. It was endothermic when, for example, you put it in the flame and it gained all that energy to make the electron go from a lower energy level to a higher energy level. This energy will come off in the form of a photon of light, which, as we talked about, is basically sort of a wave, as energy is basically moving through space. And the wave, as we talked about, has some characteristics. We have our wavelength, we also have our amplitude, we also have our frequency. And as we saw, depending on sort of where the wavelength comes off, for example, it could correspond to somewhere in the electromagnetic spectrum that we saw. And the sort of relationship of a wave and sort of energy and wavelength and frequency is, again, if we have a longer wavelength, we typically will have a lower frequency. And that usually is a lower energy type situation that's occurring. And that's different than if we had kind of a shorter wavelength. We typically will have a higher frequency and a higher energy. And again, if it does come off, for example, the wave in the visible part of the electromagnetic spectrum, again, that is where we see colors like our red, orange, yellow, green, blue, indigo, and violet. And even within the colors, as we talked about, there are differences in terms of energy. Again, red would have a larger wavelength or a longer wavelength than, say, purple. And again, would have a little bit higher energy, violet versus red in that situation. We talked about that. We can sort of calculate the wavelength or the frequency if we know one or the other, and we can use this formula to do so. C, which is the speed of light, is equal to the wavelength times the frequency. The speed of light is a constant, meters per second, 2.9979, I think was the number we used, times 10 to the 8, or 3 times 10 to the 8 meters per second. That means that when you do use your wavelength, it does need to be in meters. Remember that a frequency is typically in reciprocal seconds, or 1/seconds, which is also a hertz. And that's how we get to those meters per second. So you can use this formula to solve for either the wavelength or the frequency. It is the same calculation regardless, basically, which one you're solving for. You're going to take the speed of light divided by the frequency if you want the wavelength. If you want the frequency, you're going to take speed of light and divide it by the wavelength. So it's basically the same sort of calculation. We saw that at the end there, we could also sort of calculate the energy associated with these waves that are coming off through E is equal to H times the frequency. H here is another constant, that is Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. And obviously the frequency there is our reciprocal seconds. Sort of tying both of these equations together, we can tie those guys together. Thank you very much. And we can do so through frequency here. And since frequency is equal to c divided by the wavelength, we could substitute into that equation hc divided by the wavelength. And that does give us sort of an option of, if we do know the wavelength, we could calculate the energy associated with that wave. And also, obviously, if we know the frequency, we could also calculate it. So it does give you a little bit of an option. The other sort of main thing that we sort of talked about a little bit and touched a little bit upon it today as well is the idea of energy and this idea of quantized energy versus maybe non-quantized energy. So remember, when we have sort of quantized energy, which is essentially how sort of these electrons move, as we've been talking about, as we'll see a little bit more today as well, these electrons will either gain or sort of lose enough energy to, again, fully sort of transition from one energy level to the next. They will not find themselves sort of between energy levels or anything like that. So they will definitely gain and lose energy associated with that via this equation here, basically, and that is what we got going on there. And the idea of quantized energy is, as we talked about, kind of like a staircase sort of example. And again, as we talked about, if you're walking up or down steps, you'll have enough energy to be on one step versus the other step. You won't typically just kind of stay in the middle or anything like that, or stop between steps. So electrons as well sort of gain and lose energy in that sort of fashion, that they will have enough energy to kind of fully transition from one energy level to the next. And that's different than, say, something like the sun, which gives a more continuous type of energy spectrum. And when you think about like more of a continuous spectrum, as we talked about, it's more like if you're walking, for example, like up a ramp. And if you're walking up a ramp, you literally could just stop anywhere you want along the way and you'd be fine. You wouldn't fall and stuff like that. And so what we typically see in that type of situation is a different type of spectrum. We see a more continuous spectrum where like basically all the colors, for example, come out at once, as opposed to here in a quantized system, like we'll see today in lab, you will see distinct lines that will come out. And each of those lines represent basically an electron that's transitioning from one certain energy level to a next. It will give off a certain amount of energy to do that. That's going to correspond to a specific wavelength, and you will see a specific line associated with it. Any questions on that there? Okay, so I think we finished, or we did this example at the end, right? Is that the one we finished up on, I think? Yeah. So I think, or maybe on this example, I don't think we did this one, correct? Right? So why don't we do this one? What is the energy in joules with a wave that has a frequency of 2.8 times 10 to the 2.87 times 10 to the 14 reciprocal seconds here? Okay, let's take a look. So in this case, we have a frequency which is 2.87 times 10 to the 14 reciprocal seconds. We are looking for the energy. So that energy that has the frequency in it would be a good equation to use there. Remember, again, h here is a constant, so that's Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. So really, in this case, we just got to plug and chug into that equation there. So 6.63 times 10 to the minus 34 joules times seconds. And we're going to times it by our frequency here, 2.87 times 10 to the 14 reciprocal seconds. In this particular case, our seconds will cancel each other out, and we will be left with joules. Once again, as we talked about last time, you definitely want to make sure you are using your exponent button when you punch this stuff in, and you'll end up with maybe something like 1.9 times 10 to the minus 19 joules in this case. Any questions on that calculation there? All right, let's take a look at a couple more here, maybe a little different ones-ish. We want to calculate the number of photons in a laser pulse with a wavelength of 337 nanometers and a total energy of 3.83 millijoules. A couple of things that might be helpful here. Nano, again, is 10 to the minus 9. Milli, 10 to the minus 3. And in this particular case, since we're talking about photons and a laser pulse, our total energy is equal to the energy of our photon times the number of photons. So that's a good relationship there. All right, so let's take a look. So in this particular case, we're looking for the number of photons. So this relationship here, if we know the energy per photon and we know the number of photons, that'll give us our total energy. So we are looking for basically this guy. We do have the total energy given to us, which was 3.83 millijoules. So in order to figure out how many photons we need, the one thing that we can solve for, or eventually need to figure out, is the energy associated with one photon, basically. And we could do that because we are given a wavelength, right? So if we have the wavelength, we could basically figure out the energy that's associated with that. So we could use our equation to do that. We could go E is equal to h times the frequency, and substituting in for the frequency, that gives us this version here of the equation, our hc over the wavelength, which basically means all we need is the wavelength to figure out the energy, which we do. As we talked about last time, we do want to be careful, right? We want to be careful of units. So super common nanometers here in terms of wavelength. We do need to convert that to meters always when you kind of go into this formula. And that's mainly because of C here, which is in meters per second. So everything cancels out correctly. Otherwise, again, you're going to be off. So we'll do that conversion first. Remember that when we do see the nano like that, that means in 1 nanometer, there is 10 to the minus 9 meters, or 1 times 10 to the minus 9, which is basically scientific notation. So we'll go 337 nanometers. We'll do that little conversion there, 1 nanometer, 10 to the minus 9 meters. That's going to get us here. I'll punch it in right here. Clear that. 337 times 10 to the minus 9. It's going to give us a 3.37 times 10 to the minus 7 meters. Again, h is a constant, so that's our Planck's constant, which we always have, 6.63 times 10 to the minus 34 joules times seconds. And so is the speed of light. So again, I'm going to roll with the 3 times 10 to the 8. If you want to use the number we saw last time, perfectly fine, 2 point, whatever it is, 9979. I can never remember how many nines. That's probably why I don't use it. Times 10 to the 8, you can use that as well. So going into here, our E is going to equal our, everybody on top is basically a constant. So 6.63 times 10 to the minus 34 joules times seconds. Our 3 times 10 to the 8 meters per second. And we're going to divide it by our wavelength, which has been converted to meters. So everything cancels out correctly. The meters will cancel. The seconds will cancel. That's going to leave you units of joules, which is good because that is an energy. And we, again, definitely want to use our exponent button here. So 6.63 exponent button, negative button, 34 times 3 exponent button and 8, hit equals, divided by 3.37 exponent button, negative button, and 7. And that's going to get us essentially our energy per photon, which is what we're figuring out here, basically. Based on that wavelength of something like 5.90 times 10 to the minus 19 joules. First off, any questions so far on that part of the calculation? Yeah. Yeah, you should do appropriate sig figs along the way here. So everything looking like 3 here, so 3 is probably appropriate for this sort of answer. Now, this again is really not the answer we're looking for in this particular question. This is really an answer that we need to get to what we're looking for. And that is because we are looking for basically the number of photons. So we just calculated here the energy per photon, and we have the total energy. So if we use that relationship, we will know that the number of photons will basically equal our total energy divided by our energy per photon, basically. And that's basically just taking this and dividing it to the other side, basically. Once again, we do have to be careful of units, right? Our answer per photon here is in joules. The total energy is in millijoules. So again, we need to do a conversion to get everybody into the same unit so that they cancel out correctly. I'm just going to take the millijoules here into joules. So I'll go 3.83 millijoules. You could use the 10 to the minus 3 if you like, or there's 1,000 millijoules in a joule. You could also use that conversion if you want to, like 1,000 milliliters in a liter works the same way. So you could do that as well. So we'll go 1 millijoule is 10 to the minus 3 joules. That's going to give us our total energy in the correct units, hopefully. And I'm going to do that. And that's going to get us 3.83 times 10 to the minus 3 joules. So that is our total energy converted to the right units. We're going to divide it by the energy per photon, which is 5.9 times 10 to the minus 19 joules. And that's going to give me a lot more numbers than probably I could put in that space. So we'll move it over probably 5.9 to the minus 19. That's going to get me something like 6.49 times 10 to the 15 photons. Yeah, that's a lot of photons. Yeah, just providing that much energy. Any questions on any part about there? So sometimes in these chapters, you will see, just kind of talk about, how many photons or this number of photons and that type of stuff. And that's a nice little sort of formula that kind of ties, again, the total energy to the number of photons and the energy per photon. Any questions on that one there? All right, let's try one more here. What is the frequency of radiation that's required to supply 1 times 10 to the 2 joules of energy from 8.5 times 10 to the 27 photons? There we go. All right, so let's take a look, see how you're doing. So in this particular case, again, we have kind of the number of photons here. And we have basically our total energy. So again, we could use that sort of relationship we just saw there, that our total energy is our energy per photon times the number of photons. And in this particular case, we have this, we have this. So once again, it would make sense perhaps to figure out the energy per photon from that information. That's helpful because we know that the energy is equal to h times the frequency. So once we have the energy, we could get ourselves over to the frequency, as h is a constant. So that's sort of the pathway there. In this case, we're all good in terms of units. Nothing's really in the wrong units. So we're going to divide that to the other side, and that will give us that the energy of a photon will basically equal our total energy divided by the number of photons. And again, that's going to give us basically the energy per photon. And if we pop our numbers in there, we got 1 times 10 to the 2 joules divided by 8.5 times 10 to the 27 photons here. And again, using our exponent button and dividing that there, 27. That's going to give us something like a 1 point, I'm not going to round just yet, 1.18, too much, minus 26 joules. And that again is our energy basically per photon. So now that we have basically our energy per photon, we can use Planck's constant, which is a constant in this case, 6.63 times 10 to the minus 34 joules times seconds. And we could rearrange this equation and solve for frequency. So we're just going to divide that to the other side there. And that will give us the frequency we're looking for. And the frequency here of our photon basically is going to be our energy per photon there. And we're going to divide it by our Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. The joules are going to cancel. I know I wrote a rounded number there, but I am going to go with just the whole number in my calculator that I got from the first calculation. I'm going to divide it by 6.63 to the minus 34. And that'll get us something like 1.8 times 10 to the 7. Here, the units would be reciprocal seconds. It's basically 1 over seconds when we divide the bottom to the top in this case. Any questions on that one there? So that's sort of a little wrinkle on these sort of wavelength energy type of calculations, where again, maybe you might have to do something with the total number of photons along the way. Question on any of that. So obviously you do need to be able to calculate wavelength, frequency, energy associated with all these things. Any questions on how to do any of that there? Okay. All right, so now we know how to calculate some of this stuff. Let's continue on here. Actually, we got one more to go here. This is to relate to our electromagnetic spectrum that we talked about. So we want to put these guys in order based on wavelength, frequency, and energy. Microwaves, gamma rays, green light, red light, and ultraviolet. So take a moment, as we talked about last time, you're not responsible necessarily for the exact numbers where all these breaks off, but you do need to be able to kind of do a question like this and kind of put them in order. So take a moment and put them in order those three ways. All right, so let's put these in order. So again, shortest wavelength here should be gamma. Yeah, that was the far end of the spectrum. The next shortest, I would say, would be UV. Right, it's just to the left there, the visible spectrum when we looked at it. Now, the visible spectrum would actually come next, which is where we would see, obviously, our colors come out. And as we talked about, red has a longer wavelength than all the other colors. That would mean that green probably should be next, followed by red and microwaves. We're down at the longer wavelength part of the spectrum. Yeah. Any questions on that one? That means by frequency here, we're looking for our low to high frequency. So obviously here, this is our shorter wavelength, and this is our longer wavelength. And what we know with longer wavelengths is it has a lower frequency. So basically, it's the exact same order, just opposite, right? So our lowest frequency here should be microwaves. We then should have red, green, UV, and then gamma, right? Gamma with the shortest wavelength should have the highest frequency out of all those. And the relationship that we talked about, right, is energy is related to wavelength. So the shortest wavelength would have the highest energy, and the longer wavelength would have the lowest. That means that this order would also be the same there for both of those. Yeah. So again, our microwave having the longer wavelength, the lower energy, gamma rays having the shorter wavelength and higher energy. Any questions on that one there? Yeah. I'm going to say a little bit of both. So you do need to know kind of the breakdown, like this type of question. And I would hope that you would understand, like we were just kind of talking about, the relationship again between the shorter wavelength and the higher frequency and the higher energy. That's, as much of an explanation as you might need to give. Yeah. Other questions? All right, so let's continue to talk about. We were talking about a little bit before we got into these calculations there. Einstein, and remember Einstein sort of the photoelectric effect, where they shine light on metal, and they saw that electrons would basically be able to, once you got over that sort of threshold frequency, be ejected from the surface of the metals. So again, when irradiated with photons with shorter wavelengths, those electrons absorb more energy than is necessary for them to escape. This excess amount of energy becomes kinetic energy of the electron as it gets ejected off. And you could calculate the kinetic energy, which we're probably not going to do, by taking the photon minus the binding energy associated with it. But one of the things we were talking about again, and as we saw with our flame test and sort of been talking about is, again, as these atoms sort of absorb and release energy, we do have electrons transitioning from different wavelengths. And depending on when that light is released, again, that is, as we talked about, sort of why we see colors when we see fireworks, neon lights, and obviously, like when you do sort of, flame tests, you do see some colors. There is what is referred to as an emission spectrum. So when the atom releases that energy as those electrons are transitioning from a higher energy level to a lower energy level, that will release basically an emission spectrum. Um, when we pass light through a prism at a particular wavelength, we do see a unique sort of spectrum, and it's a non-continuous spectrum. And there's some neon lights from your book. So scientists in the late 1900s sort of struggled with the idea of light being emitted from atoms and molecules. And they did sort of notice two separate sort of spectrums, as we've been sort of touching upon. Again, this more continuous spectrum where basically we just got everybody coming off, at all wavelengths and stuff like that. So when solids, liquids, and gases are heated enough, they will radiate a lot of this excess energy as light and give that continuous spectrum, which again, if you do look at it through a prism, it'll be more like a rainbow type of effect. And that's again more like as we were talking about in terms of energy, walking up sort of a ramp where again you can basically just stop anywhere along the way. Now, in contrast, we do see when we heat uh, gases of elements, we do see a more line spectrum that does occur. And again, that line spectrum, as you will definitely see today, are these narrow lines at specific wavelengths and specific um, parts of the visible part of the spectrum. And again, you could do that with an electrical discharge tube by running electrical currents, going to excite the electrons in the element in their gas phase, and you will see that. Line spectrums from elements are so specific that you could actually identify the element you're dealing with by what lines you see, what wavelengths they come out at, what colors you see. Every element will have its own sort of unique line spectrum. As you'll do tonight, you will try to identify an unknown based on, what colors you see, what lines and wavelengths that you see basically come off. Now, when we have an emission, we see that single wavelength of light. And again, this is implying that we're seeing basically these electrons transition in these quantized way in terms of energy. As I mentioned, we will never sort of find an electron, as I mentioned, just kind of hanging out in the middle there. It's either going to make it all the way there, going to make it all the way there. It's just not going to kind of stop halfway through. And because it requires a certain amount of energy to do those transitions, when the atom releases that in its emission spectrum, it will correspond to a specific wavelength. So you'll always, for example, in like hydrogen, you will always see a specific set of lines that will come out, and those correspond to specific electrons making the same sort of transition from one energy level to the next. That's going to give off a certain amount of energy, which will correspond to a specific wavelength, and that's going to correspond to your lines that you see. Now, when we talk about Rutherford's sort of model of the atom, which we'll talk about actually in the next chapter, but you probably are familiar with it from previous class. As you may know, right, Rutherford basically found a more nuclear model of the atom where we have a nucleus, where we have protons and neutrons basically in there and electrons flying out in basically the empty space. Now, the idea of this is the electrons don't fly away because of the opposite attraction between the negatively charged electrons and the positively charged nucleus. And as those electrons are moving around in that empty space, there is sort of a problem in terms of an energy component of that. So, according to classic sort of physics, as particles like electrons start to move, they should be sort of losing energy basically along the way, which means eventually, if they will lose energy, crash into the nucleus, and there goes the atom. And that's obviously not what's happening in this situation. So, to try to explain some of this, one model of the atom that sort of came about was one that was done by Bohr. And Bohr's model of the atom is oftentimes referred to sometimes as like a planetary model of the atom, where we have basically a nucleus here that has our positive charge. And then we have several terribly drawn circles there. And each of these are what are referred to as orbits. And the idea in sort of Bohr's model is we have these electrons that are going to be in these nice little orbits around the nucleus and traveling around in nice, pretty patterns like that. We know for sure sort of where they're at. You just think about if you put your finger there, eventually it'll come back around, right? And you'll run into an electron. And this was sort of the idea. Now, one of the restrictions of Bohr's model was this quantized idea that the electron had to be either this orbit or this orbit or this orbit. Once again, we wouldn't find an electron just kind of hanging out in between orbits or anything like that. And as the electrons sort of traveled from one orbit to the next, they would also gain and lose energy in a quantized fashion. So they would be able to move from one orbit completely into another orbit, again, not finding itself sort of trapped in between along the way. And this quantized model and Bohr's model of the atom worked really well to describe sort of the line spectrum that we see in something like hydrogen, which has basically one electron. As you may know, when you talk about a theory, which is really what Bohr's model is here, theories are not necessarily correct in all aspects. And one of the things, as we will see, is we do move away from Bohr's model of the atom because it works really well for hydrogen or hydrogen-like atoms that have, kind of like one electron. But as you get a bunch of other electrons involved, there's other factors that are sort of involved, and it doesn't really hold up very well in terms of what we see in those situations. One of the situations is obviously we got a lot more electrons in there. You got a lot more negative things near negative things, which don't like to be near each other, right? So opposites attract, right? And things with the same type of charge don't like to do that. So as we talked about, Bohr's model is that sort of orbital type model where these orbits, we have these different sort of energy levels, which are sometimes referred to as n, and that's the principal quantum number. And n equals 1 is the ground state in energy. And n from 2 to 7 are what are known as excited states. So n itself is known as the principal quantum number. We're actually going to talk about quantum numbers here in this chapter and the different types of quantum numbers, but you could think of n really as like the energy levels. So n equals 1 is the ground state, which is usually the most stable in terms of energy, is also the one that is normally closest to the nucleus. And as you go to like n equals 2, n equals 3, and so forth, you're getting higher in energy. You're also moving further away from the nucleus. And, in the case of Bohr's idea, when we kind of look at this, this would be like, n equals 1, n equals 2, and so forth. And when we look at sort of a line spectrum for something for hydrogen, what we see are some distinct sort of lines that occur, like say blue, red, and green. And again, these are basically a result of electrons transitioning downward from different energy levels. And as you can see here, our blue is a result maybe of the electron going from the fifth energy level to the second. And that's a lot more energy transition, right? Difference in energy than maybe this guy here. That's more of a red line that you would see that's only maybe transitioning from the third energy level to the second. Again, the relationship between energy and wavelength, right? The higher the energy, the shorter the wavelength. So this transition here, which is a lot more energy, which will give you a lot more energy output from the atom, would result in a shorter wavelength of color coming out. And remember that towards the blue-violet part of the visible part of the spectrum is where we see the higher energy colors coming out, as opposed to here where maybe it's just transitioning this little bit of energy, which would allow the atom to release that amount of energy, which is a smaller amount of energy, which would correspond to a longer wavelength and more of the red part of the spectrum. So as we talked about a little bit last time as well, when you see these sort of line spectrums, you could make a rough estimate as to maybe how much that electron is transitioning or how far that electron is transitioning based on the colors that you see. If you see more of the blue-violet type colors in that region, you're probably got electrons transferring a good amount of energy levels, rather than if you're on maybe the red and orange part of the spectrum there, is probably an electron maybe not transitioning as far down in terms of energy. And again, as you can see here, that's the idea of those orbits. And it is a quantized sort of model. As I mentioned before, they will definitely gain in energy and lose energy enough to fully transition from one orbit or energy level to the next. And as I just sort of explained there, you can see those transitions is going to correspond to the specific colors that we see in something like hydrogen here. And it worked really well, as I mentioned, to sort of explain what we see with hydrogen. But as I mentioned, sort of Bohr's models we'll talk about really did sort of break down as you kind of move away from one electron sort of a situation. Here is an example of some different sort of line spectrums. And again, you can see, much like you'll see tonight, you'll see some different lines coming off. And each of these lines do represent basically electrons transitioning different wavelengths, or different energy levels, giving off energy in the form of a different wavelength, which comes out in this sort of spectrum. And here is hydrogen and the difference between a continuous spectrum. I think maybe the next one, this one. So we'll take a look here. Maybe.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
And as we saw here in sort of this picture here, you can see white light again, going to give you a more continuous spectrum coming here where we see all the colors coming off. Much like we were going to do tonight, hydrogen gas here going through a prism will be separated out into these specific quantized sort of lines that we see, as opposed to basically on the top there, we got everybody coming out, all the energy sort of levels, if you will, versus there we have very specific discrete amounts of energy coming off that correspond to those specific lines that you see in those spectrums. Now, Balmer was able to basically derive an equation that allows you essentially to calculate the energy associated with when an electron sort of transitions from one energy level to the next. And this is one of the ways sort of his equation is here. This equation relates to 4 visible wavelengths of light that's emitted by hydrogen. And we do see other discrete lines in hydrogen are found in the UV and IR spectrum. And that's also something that you should keep in mind. A lot of times we do talk about when electrons sort of transition, you know, the colors that you see, this sort of colors that come off in an emission spectrum. Not all transitions will come off in the visible part of the spectrum. So again, if there's an electron transition that's outside the visible part of the spectrum, you will not see, you know, colors coming off. It may be like in infrared, and maybe that's something to do with heat, maybe in like the UV region as well. So they're not always going to basically happen there in the visible part of the spectrum. But we do oftentimes look at the visible part of the spectrum, obviously, because we can see colors, right? And that's easy to identify, things like that. You will also see sometimes some of the lines will be much more intense when you look at it through a prism or spectroscope. And that's also because you got to remember sometimes we think about things sort of singularly, like, oh, it's just one electron, right? But if you had hydrogen atoms present, right, there is a lot of hydrogen atoms present, right? And each of those hydrogen atoms are having electrons doing transitions. And you could have multiple ones going from the same energy level, right? And transitioning to the same sort of level. And that's going to give you a more intense color, and probably in the spectrum there than maybe something where there's not as many of those electrons transitioning. So sometimes when you look at it, you'll see ones that really pop out a lot more or a lot darker in terms of color. And that's a result of multiple electrons sort of transitioning at the same time in the same energy level. Now, again, Rydberg sort of generalized Balmer's work here, and he came up with sort of this relationship here of 1 over the wavelength is equal to Rydberg's constant 1 over n squared, which is our energy levels, minus 1 over n squared, our second energy level. Now, Rydberg's constant, you'll sometimes see in your book, we'll use sort of this version of it as sort of a wave number. Most people will use Rydberg's constant as joules, like we'll do in lab, and that's 2.178 times 10 to the minus 18 joules. Or if you want to abbreviate that down to 2.18 times 10 to the minus 18 joules, that's good. So you can think of that as sort of a constant, and that's usually more so the number that we use in this class is joules for energy. We don't use anything like electron volts or things like that. We do typically calculate things kind of in joules and stuff of that nature. So a couple of important relationships are these equations here, and let's just talk about these here. First off, up here is the equation that you can use to basically find the energy change that occurs as an electron goes from one energy level to the next. And this is one version of it. Once again, this is Rydberg's constant. That's that 2.18 times 10 to the minus 18 joules. This is the final energy level that the electron ends up at, and minus basically the initial energy level. And those energy levels are squared. So you do need to square them. And there is a negative here. and that will allow you to calculate the energy change that occurs. Now, this energy here is the same energy that we saw earlier, and that's also equal to h times the frequencies like we saw earlier, and that is also equal to hc divided by the wavelength. So all those equations do tie into that energy change, and it kind of works the same way. Now, when you do calculate energy, there is a couple of things that's kind of important here. First off, energy can be positive or negative, and it is important to keep it positive or negative. If you have a positive value for energy, that is typically an endothermic process, and that is where energy is absorbed. If you have a negative value for energy, that is an exothermic process, and that is where energy is released. So that is also a very important sort of aspect of it. So whenever in this class you are calculating energy and you end up with a negative number, you should keep it negative, provided you calculate it correctly. It should be negative because it tells people what's happening. It's exothermic. How does this relate to our electrons? If I have an electron on a lower energy level and it goes to a higher energy level, is that going to be an endothermic process or an exothermic process for the atom? It is going to be endothermic. The atom has to gain energy to allow the electrons to gain that energy to go to a higher energy level. So if you're doing a transition where your electron starts at a lower energy level and ends up at a higher energy level, when you calculate energy, you should end up with a positive number. You should end up with an endothermic positive type value. If the electron is going in, they have opposite direction, say a higher energy level to a lower energy level, the atom has to release that energy, and that's going to be an exothermic type of process. And when you calculate the energy associated with that, you will end up with a negative value and stuff like that. And that's what you should do. So definitely when you're calculating energy, you want to make sure keep it positive or negative, depending on what you get, because it is actually important to let people understand, are you dealing with an exothermic process or an endothermic process in that case? By the way, in this version of the equation, um, this is a little bit opposite of what's on the other page. The negative has been distributed outside, and that just makes it work correctly as well. You'll sometimes see this equation with the no negative on the inside and the two guys switched around as well. Again, the negative is just kind of put back in there. Now, you could use this equation again if you know in, say, hydrogen, where the electrons are transitioning from what energy level to next. You could figure out the energy associated with that transition. You could also figure out the frequency associated with that energy and the wavelength associated with that. So you can calculate all those things, which you will do tonight. Now, this equation right here is basically kind of like the same equation. E of n is equal to minus 2.18 times 10 to the minus 18 joules z squared over n squared. This is basically the energy associated with an electron on a specific energy level in hydrogen. So if you know what energy level your electron's hanging out at, you will know how much energy is associated with it on that specific one in the hydrogen atom. Z here is the atomic number, and that is the number of protons, which you can find on the periodic table, and that is the number above the symbol. And if you wanted to do it for hydrogen, that is why there is a 1 up on top, because it has 1 proton. So 1 squared is 1, so 1 over n squared for hydrogen. You can figure out the energy associated with hydrogen. Now, a lot of times we do use these with hydrogen, but you can use it with some other elements as well. And sometimes you'll see weird ones like He plus, which also, because it is plus 1, it has 1 electron. So again, it works very much like a hydrogen. So there's a number of ions that are hydrogen-like ions that have 1 electron, and you can sort of apply that to this as well. These are 2 equations that we will definitely use in about 40 minutes. Yes, when we go to lab and stuff like that. Any questions on that? With that being said, maybe we should try, make sure we know how to do it. What is the energy in joules of a wavelength in meters, and the wavelength in meters for a hydrogen spectrum that moves from the fourth energy level to the sixth. And in what part of the electromagnetic spectrum do we find this radiation? Well, we just work on the calculation part first. So we're looking for the energy associated with this transition and also the wavelength. So take a few moments there and see what you come up with. Okay, let's take a look since we're getting kind of to the end here. We have some different energy levels. So our initial is the fourth energy level, and it's going to end up on the sixth. So clearly that's all we're given. So we do want to use obviously the formula that has the electron transitioning. So that is the one we just saw there with Rydberg's constant, minus 2.18 times 10 to the minus 18 joules. 1 over n squared final minus 1 over n squared initial here, I believe. And again, we're going to pop into here our minus 2.18 times 10 to the minus 18 joules. That's going to give us 1 over 6 squared, which is 36, minus 1 over 4 squared, which is 16 in this case. And if I do that, 1 divided by 36 minus 1 divided by 16 times my 2.18 to the minus 18, that's negative. That's going to get me an energy of like 7 point, I'll go 2 decimal places, 57 times 10 to the minus 20 joules in this case. First off, any questions on the energy calculation? Now, yeah. Correct, yeah. So in this case, we talk about the change in energy because it's really talking about the electron transitioning from one energy level to the next. So that's basically the electron change, which ultimately will be sort of, either absorbed or given off by the atom as it goes there. Speaking of that, our number here for energy is a positive number. That makes sense, right? Because our electron is starting at a lower energy level, right? And going to a higher energy level. So this is the process where the atom is absorbing that amount of energy to allow the electron to make that transition. Again, if we ended up with a negative value for energy here, which would happen if we switched it around and our electron started on the sixth energy level and ended on the fourth, it would be the exact same number. The only difference is it would be negative. And again, that's sort of that quantized energy, right? So going from 4 to 6 is a certain amount of energy, or dropping is the same amount of energy. In that case, the energy would be released by the atom. As I mentioned a second ago, energy you should keep positive or negative depending on what you get because it's important. One thing that you should also keep in mind is in a question like this, where maybe we're looking for the wavelength, which again, this would equal h times the frequency and also hc divided by the wavelength. So essentially, this is the same equation that we used earlier, and we're just going to use the change in energy in this case for our energy in this particular case. Now, in this particular case, we're okay because our energy is a positive value. But if you do come across a situation where your energy is negative, you need to make it positive when you go calculate something like wavelength or frequency, because the wavelength and the frequency should be positive numbers. So that's a very common thing, especially when we talk about electrons transitioning downward. You will get a negative value for energy, but you should not have a negative value for wavelength or frequency. So for lack of a better description, all you have to do is just make it positive. Yeah. So when you get to wavelength or frequency, number is going to stay the same. You just need to make it positive. That way you'll end up with a positive wavelength and a positive frequency. In this case, because it's an endothermic process, we don't really have to worry about that. Our H and our C here is our same H and C that we used previously. That's our Planck's constant, which after tonight you'll be very familiar with, and our speed of light as well. So popping those numbers in, we got 6.63 times 10 to the minus 34 joules times seconds. We got our speed of light times 10 to the 8 meters per second. And we have our wavelength. I'm sorry, I should really rearrange this before I do that. That probably would have been a much better move. So we will have our energy on the bottom, which would be 7.57 times 10 to the minus 20 joules. Again, if we rearrange this, which probably would have been the better move, we're going to multiply our wavelength to the other side, and that's going to give us our wavelength times our energy is equal to h times c. We're then going to divide that, which will give us our wavelength is equal to hc divided by our energy in this case. So this is obviously our wavelength over here, as we can see with our units. Joules are going to cancel, seconds are going to cancel, and we are going to be left with meters in this case. And calculator would be good. I'm going to go 6.63 to the minus 34 times 3 to the 8. I'm going to divide it by the energy, and I'm just going to use the whole number in my calculator. I'm not going to really use the rounded number or anything like that. And that's going to give us a wavelength here of, we'll go 2 decimal places, 2.63 times 10 to the minus 6 meters. And once again, when you are calculating wavelength or frequency, they should be positive numbers. So again, sometimes you do have to kind of just convert your energy value into a positive number so you don't end up with negatives on the infraredish area of the spectrum would be here, IR, yeah, in that sort of range. Question, yeah. Because that's the formula, if this is what you're asking up here. So that's the formula that you would use to calculate the energy associated with an electron transitioning from one energy level to the next. And if you think about the problem here, that's basically all we had was the energy levels, right? So this is a constant. That's the Rydberg's constant, that 2.18 number. So that's just like a constant value. That's part of the formula. And like I said, in your book, they will, I think in this new book, they do kind of use the 1 over the wavelength, or you kind of see Rydberg's constant as 1 over the wavelength, basically. If you do the conversion between 1 over wavelength and joules, it comes to the number that we commonly use here in this class. So that's that 2.18. The 7.5 times 10 to the minus 20? Yeah. Yeah, so I just clear it here. So basically, this is what we had, right? And so we had our E, which is basically equal to HC over the wavelength, right? So we were looking for wavelength in this case. So we do need to multiply the wavelength of both sides. They cancel. And that gives us HC equals E times the wavelength. And since we want to isolate the wavelength, we have to bring this back over to divide. And that's how it gets to the bottom over there. Yeah. Yep. Yeah. What's that? It would be this equation right here, and this would be if you were wanting to calculate the energy associated with an electron on a specific energy level, not transitioning from one energy level to the next. It has a certain amount of energy based on what energy level it's at. That's what you would use that equation for. Yeah. Yeah. Other questions? Okay, so I'm just going to say this next example just to save some time next time. If you could work through this next example, and we will go over it at the very